Hi. Well, I think most of you know me. My name's Dr. Stephen Fenton. There's a couple of people that don't, so I'll just introduce myself. My talk today, excuse me, is to do with punch metering, and there's a little bit more than punch metering. So we've been experimenting with some other measures, which I'm also going to talk about towards the end of the presentation. So just a little bit of research background. The whole idea of measuring punch was to investigate and find new metrics to quantify perceptual measurements or perceptual elements within mixes and complete stems. So things like punch, clarity, warmth. These are all semantics that get bandied around and used by musicians and engineers, but there aren't specific measures that we can, or objective measures that we can use to quantify mixes in audio in using those terms. So on an application basis or an applied basis, these metrics that we're investigating can be utilized in auto mixing tools, auto mastering tools, etc. And the tool I'm going to demonstrate today is a sort of a byproduct of the metric. So it's a punch meter. So punch, I mentioned this as a semantic term. It's often used. People use it loosely, and it can often mean different things to different people. So loudspeaker manufacturers, it can mean something slightly different than, say, a producer or an engineer. If you look into formal definitions, if you try and find them, there are some. The development of a sound wheel for reproduced sound was pretty much the only defined definition that I could find for punch. And that was back in 2015. So I attempted to formalize it at the back end of this research. I formalized it. This is my formal definition of what punch is. And really, it just says that it's a combination of transient change and energy density at a particular moment in time. So if you have dense energy and it's changing quite a lot, then this can create punch. But at this point, nothing was defined in terms of what the parameters were. So how fast energy changed, across what frequency, how would we sum all that together in order to give us this overall punch score, which was the main focus of the research. So we did a load of subjective testing. We produced a model and we compared the objective model outputs with the subjective data. And this was published in, I'll call it the key publication, the sort of the final publication of the model itself, was published in 2019, and it was in the JAES. And there was it was included in a feature with Rumsey and a feature interview. So just a bit of background in terms of what happens in the model. This is the model that's the model equation that's outlined in the paper. So we have a multi-stage system where the audio comes in and it gets separated into what we call the transient, the steady state, and residual elements. And we apply some spectral weighting filters. So these are the psychoacoustic filters, essentially, that are modeling the ear. And then we go into an octave band filter arrangement. So this is, again, looking at the subband analysis that we generally, when we model an ear, this is the approach that we can adopt. And the model equation just basically looks at the onset times in certain bands. It looks at the frequency, the energy within certain bands, and it sums all the energy up depending on the weighting of the onsets that are detected and the frequency bands, and we get a overall punch frame score. If we look at the score, the model output compared to, say, a standard ITU loudness model, this audio sample here if we look at it at the standard loudness model, it looks like the plot on the left. So you can see you can't really tell that much from that output. Of course, the loudness model as such wasn't designed to give us any further indication of attributes of the audio except the overall loudness. But if you look at the plot on the right, this shows you the punch output. So you can see when there are elements of punch and when there isn't. And you can also get an indication of the underlying dynamic that exists within that particular audio sample. So you can clearly see where the kick is and the snare and the kick and snare as the track progresses. What we can do is when we collect all these punch frame measures, we can analyze them statistically across the entire program. So this is the equivalent of, say, program loudness. And we can then get through a histogram and percentile plot, we can begin to see differences between songs. Now, this is quite interesting because all the plots, all these three songs here have the same overall loudness. But what we can do is we can begin to see differences between the tracks. So these three tracks are. So this is the Well-Droid song. That's the Well-Droid song. The second one. Oops. Bring that shit in. And the third one. So all three tracks have similarities in terms of these bottom percentile punch scores, but only above, say, 70%, we begin to see a differential between the highest punch frames and the lowest punch frames. So you can differentiate between the two. The punch tool itself, we show this differential in this window on the right-hand side here. This shows the histogram plot, how you'd visualize loudness, but these are what's important. The difference is these are punch frames rather than loudness frames that we indicate. These meters on the left here, we've got a timeline plot, and we're able to select whether we want to see the transients, the steady states, significant hits, etc., etc. So the real-time implementation differs slightly to the original model in terms of the separation system and the onset detection, but only subtly. But what we did find is when we retested the real-time implementation, it performed better than the original model. So through work that Andrew Parker did, he was working when he was a master's student. He did a lot of work on the separation and the detection system, and the model improved as we went along. So this has the plugin that's available now has this final implementation. So the transient extraction, originally we were using median filtering to perform the transient steady state separation, but now we advanced it a little bit and we use Euclidean distance deviation, which takes in both the magnitude of the bins and the phase of the bin as well. Because as you get a transient signal, you get a lot of change in phase information as opposed to a steady state. So what you can do is weight the magnitude with the phase information, and you can get better separation as a result. The onset detection is all done through weighted average, and it uses an adaptive threshold. So if you get consistently high levels of punch, then it's still possible to detect other changes as the time frame of the audio runs through. So this is different to a fixed threshold, which can end up jumping all over the place. So the statistical metrics that the original punch meter gives and the perceptual punch tool gives are the mean. So this gives you the mean punch frame score as the program runs through. Then we've got the P95, which is the 95th percentile of punch scores. We chose 95 because any what we find is 5% of the frames might be very loud, occasional frames, and they're sporadic. So you don't want those frames affecting the overall perception of the punch score or affecting the punch score greatly. So we only go up to the 95th. We don't take the full range into account. The 95M is simply the P95 score divided by the mean. And we found that the P95M gave the highest correlation to the subjective punch scores. But all the measures are shown in real time as it runs, so you can kind of choose which one you want to use or which is the most useful. So this is the UI for the punch meter itself. So you can select whether you want transient, steady state, and various other things. You can switch different things off. The tool itself splits the audio into mid-side, and we primarily do the punch measure on the mid signal itself. What that also allows us to do is manipulate the mid. So not only is this a punch measuring tool, but it's a punch manipulation tool if you want it to be. So these controls here, we can control the punch, whether we want more punch or less punch. This control here controls what I call the punch body, which is the mixture between the steady state and the transient. And we've got just standard mid-side controls here. So you can push the mid, lower the mid, push the side, etc. So that's a byproduct, which is nice. The difference here is this is a perceptual tool. So the metering that you see is relevant in terms of what you hear. And that's different to all existing measurement tools or punch manipulation tools at the moment. And also when we manipulate the punch, we're only manipulating the key bands that we investigated and found had a direct impact on the underlying punch of the audio. So again, it's not as kind of a brute force punch system. It's intelligent and it's perceptually motivated. So what we see here, there's a lot of numbers. What we've got is what we call the short-term measures and the program measures. So the program measures are if you play an audio track that's 3 minutes long, you'll get an aggregated value for the entire 3 minutes of the track. So you can do comparisons between mixes and songs and stems. And the numbers at the top will give you the running kind of real-time measure as it runs. And below it, we've introduced these new measures, which are called sparsity, significance, and trans-steady. So sparsity is where we look at the total number of frames that have a significant amount of transient energy within it. And we look at those that don't. And we deem whether the arrangement is sparse or not from that. And that gives us the ability, if we have a sparse arrangement and we have a high punch frame, we can increase the relevance of that punch frame. So it's like going from complete silence. We can detect when we've got complete silence or not, and that's graded. And if you get a sudden hit, this can be a very significant hit. So the sparsity and significance kind of work together to give us a new measure of potential clarity. Because if something's not very sparse, i.e. all the frames are full of energy, then the dominant punch frames that exist within that within the arrangement are somewhat masked or missed or can be missed out if you're not careful. So this gives us a number that hadn't existed before, which just gives us an indicator of, you know, potential masking measures, if you like. Tran and steady, this looks at the differential, this is transient steady state ratio between the transient elements and the steady state elements. So it kind of deconstructs the mix and says, okay, what's your balance? So think of it as background music versus drum mix or vocal transients, plosives, if you like. Is that ratio, are we able to differentiate well between the two? The higher the transient steady state ratio, generally the higher the punchiness of the material. So in terms of visualization, this here is showing the underlying transients of the audio along with the steady state. So I've just selected 2 of the checkboxes. This plot is showing us the mean punch score as it rolls ahead versus the short-term punch. So this you get an indication of when there's almost significant change in the audio as it's rolling along. And we can indicate by checking the significance box, because we're looking at a local, the way that the onset detection works, we look at relevant change in a short-term window compared to the wider window. So it's a statistical method at determining whether there's a significant change or onset in the audio. And what we're able to do is plot those significant changes. And we're finding that these significant purple lines, if you like, are essentially where you get the most significant hits in your audio. So if you don't see many of these purple hits, then you could assume that there isn't that many, and it doesn't, your mixes don't come across as that punchy in this system. And you'll notice below it, we've got these green bars that begin to appear. This is the transient to steady state ratio. So where you see a green bar, this is where the transient greatly exceeds the steady state. And therefore you will absolutely definitely hear those transients in that mix. So if you wanted to do it, make sure that all your drums and all, anything that possessed, was transient, and you wanted to hear it, then you try and get all these green down the bottom. Okay, so these are the sparsity and significance. These are new measures that have been incorporated as an extra to the punch that we've still got to do a little bit of say subjective analysis on, just to see whether the it's all empirical at the moment in terms of those 2 measures, but we're going to analyze them further as we move on. So here we have a video demonstration of the punch meter, and I've put it alongside a standard loudness meter, so you can see the type of information you get from a standard loudness meter at the same time, because I find it quite interesting to see what the meter gives us compared to the older meter style. There's a selection of songs, most of which, as you'll see, will have a relatively steady loudness level. So you're able to see the comparison again between the 2. And yeah, if I play these now, hopefully you can hear the differences. And there you have it. So as you could see, as the tracks were progressing, that the main line to keep your eye on was the red line, I guess, which was the overall punch score. Bearing in mind that that punch score would have been a rolling average of also all the other songs that came before it. That's why occasionally you see it sort of not change straight away and then change. So if you were playing the entire track, it would track, you know, the one that you were measuring. So it was somewhat, if we put tracks back to back, it kind of, you know, does its best to track the overall. But yeah, I hope you could see the differences there. Thank you.